Thank you for coming to this morning session. Just a brief introduction because I know that Jim here will not like a long introduction.
You're right.
But I have to say a few words anyway. So he's an IEEE Life Fellow, founding editor of Transactional Fuzzy Systems, has many awards, among them the Fuzzy System Pioneer Award, IEEE Frank Rosenblatt Award. But perhaps the most important thing is a long career in the computational intelligence. Actually, he invented the word computational intelligence because it was not clear how to join the neural networks and evolutionary computation and fuzzy system. And he said, well, look, computational intelligence. So he's very creative, and there is another word. He invented the word perfecto mundo.
It's really important.
It's a mix between English and Spanish. And then, just to tell you as well, before I forget, he developed the fuzzy CMEs. It's a very important clustering, so if you like to know more about clustering and supervised learning, he has a book, a primer of cluster analysis.
See.
And then, just to finish with a short story. Many years ago, I will not say when, because it was so many years ago, when I was a student, I attended a tutorial.
How long ago was that?
It was in Singapore.
Singapore?
Yes, and he was giving a tutorial like today.
So,
I was in the first row, that was my problem.
like these guys?
Like these guys, be aware, because this guy here.
You're in for such a treat.
And he went to me, he came, I of course I never met him before, and he said, close your eyes, put your hand like this, okay? And he put something on my hand, and he asked me, what is this? I just touch him without...
Could be anything.
Could be anything, of course, but this was in a private room.
I know what it was.
Official room.
I know what it was.
Okay.
I did it.
And I got it. I said, an apple. Manzana, an apple. And when I said an apple, he told me, that is pattern recognition. So I learned what is pattern recognition immediately. Okay.
That's it.
That's it. Okay, it's your time, please.
Now this is not going to start. Well, thank you for that introduction, and thank you for having me to Valdivia. Here we go. Do we? What?
This side. The direction.
What is it? We're not, here we don't go. There we go. Okay. Gonzalo, who is this man? How many people know who this man is? None of you. It's one of the most. Do you know?
No. Yes. No. Yes. Oh.
See,
You got it right.
you're the only one. Oh. I can't believe it. We're here in Chile. No football players. Okay. How about this one? Yeah, this thing doesn't work so great.
You have to point it like that. Point it to the computer. Point to the computer. Point to the computer.
That direction.
This is the end of my talk. You know this one? Yeah. All right, well, do you know this one? Huh. Good.
Yeah, that's right.
So, hello. So today's first talk for me is about making pictures out of data. There's only 4 topics. This doesn't work so great. I'm going to give you a short history of visual clustering, and I'm going to talk about the IVAT family of algorithms, then SIVAT, which is scaled IVAT for big data, and finally INC-IVAT, which is for streaming data. And so basically the whole talk is about making pictures. Okay, so here we go. Clustering, there are 3 problems. First, before you look for clusters with algorithms, you should decide, are there clusters in the data? So I call that problem cluster tendency assessment. The second problem is to find, after you decide how many clusters to look for, to find the clusters using whatever algorithm you have at your disposal. And I put this up. This is a little quote from a book by R.C. Robert Choate Tryon, 1939. He was a professor at Berkeley, and he published this little book called Cluster Analysis. And the reason I put it on the slide is I believe he was the person who invented the term cluster analysis. People have been doing clustering before this, but I think he was the person who actually first coined the term cluster analysis. And we'll see one of his data sets in a little while. And then lastly, after you get clusters, you can always ask, are they any good? I mean, every clustering algorithm will produce clusters at every value you ask for. And so, the algorithm doesn't know if they're any good. You, the human, have to decide whether they're any good. Or you have to use one of these cluster validity functions to try to help you decide that. I won't be talking about that today. However, I give you this quote from the 1953 paper by R.L. Thorndike. This is now we face a much nastier problem of deciding the appropriate value for C, the number of clusters. So here I use C, many people use K, it doesn't matter. All right, so this talk is about assessment of data sets before you do any clustering. Why is choosing C important? So I give this little example. And so, Pablo, now that you've learned, how do you know? I might be picking on a different. How many Pablos are in this room? Okay, Pablo. How many clusters in this data? Did he say 3?
Yes.
Jerry, Steve. How many people think that's right? Yeah, that's right. That's right. That's right. All right, so you can see 3 clusters, and the question is, do you think a computer can see 3 clusters? Because computers don't see things like we humans see them. And so here's the k-mean solution to this little tiny data set. And there it is, it's right, provided you tell it that it looks for 3 clusters. HCM means hard, C means, K means same thing. Maybe you call this algorithm k-means, Lloyd's algorithm, whatever you want to call it. What happens if you look for C equals 2? Let me just show you this, how surprising this is. This is 30 points in the plane. So, here are 2 different solutions that k-means finds for different initialization if you specify C equals 2. And here are 2 solutions different from each other that you find if you specify k equals 4. So even for this tiny, very visible, very evident set of 30 points that have 3 clusters according to us, k-means can find all of these other solutions. So you can see how fallible clustering algorithms actually are. Well, why is it so hard? Why is it so hard? Why is this so hard? Okay, so here we have a deck of cards. So on Chile, do the decks of cards have 52? Yeah. I guess only in China the decks may have like hundreds of cards. I don't know. So I can ask you how many cards are in the deck, you would say 52. If I ask you how many ranks are in the deck, you would say 13. If I ask you how many suits are in the deck, you would say 4. If I ask you how many colors in the deck, usually anyway, it's 2. If I ask you how many decks, 1. And so you see there are 5 different correct solutions to the question how many clusters are in this data set, depending on the question you ask. So this is an important point. People process data and look for cluster. They have to be careful to understand what question they want the data to answer. Right? As you change the question, the right answer changes. So that's across C, and the same thing can happen within C. I can fix this. Here's a little data set with 4 people in it, mother, father, son, and daughter. Are they all related? Sure they are. One cluster. I can also fix it up so that there are 4 clusters. If I separate them by age and sex, blood type, something like that. But look at this. Excuse me. For C equals 2, there are 3 different solutions. There could be more than 3 solutions. So the correct answer is C equals correct, so called for us, C equals 2. But there are different clusters depending on what you're asking of the data set again. So the number of clusters within C is also important. So why is it hard? Well, within group variance can be quite large. Different representations of the same object. So lots of different reasons why clustering algorithms can fail. So today's talk is trying to build images from data sets. This is just a little preliminary to see if we can decide how many clusters to look for. What I'm going to describe for you today is not finding the clusters, it's finding an estimate of the number to look for. So with that, there's a kingfish. Have you caught one? No. You think you ever will? Only if you go to New Zealand. Now I'm going to tell you the history of visual clustering as I know it. I really like history, and I guess it's because I'm an old man. The older you get, the more interesting history becomes for you, I suppose. And to me, this is the fun part of this talk. So this is a paper written by a man named Petrie that was published in 1899, so it was a long time ago. He was an archaeologist, and he was studying a collection of different artifacts and grave sites in Egypt. And he said the order of events on our planet is really the main essential ingredient of history. So he collected these 917 pieces of pottery. Sequence dates are his way of arranging the history of the collection. What's happening here? He used these 5 criteria. This is just copied out of his paper. Notice this one, number 3. Statistical grouping. This is before there were even handheld calculators. I guess they had slide rules. Jim Keller, did they have slide rules in 1899?
I don't think so.
Maybe they did. I don't even know. Anyway, it's an interesting statement to be made in 1899. And here are the pictures of them. Flash them up. You can see that on the left I show older to newer, and on the right I show the dates, 5400 BC to 4800 BC. The different types of objects are clustered both by the material they're made out of, as well as the shapes. So this was visual clustering. We just laid them out on the ground, right, and arranged them in what makes historical sense to him. I believe this is the first example of visual clustering in data. So in the more modern vein, we have 2 kinds of numerical data for pattern recognition. We have feature vectors. Does this thing work? Not really. It's okay. Relax. I thought I had a laser pointer. So there's feature vectors. Those are vectors X and RP. And there is also relational data, which are piece of information that relate pairs of objects, and that's usually not sensor data, but there are lots of relational data sets around, and we like to cluster them as well. And the methods I'm going to talk about actually end up working on relational data. Typically, positive, definite, and symmetric, but not transitive. Since you can always turn feature vector data into distance or relational data, the relational data is somewhat more general. All right, so in visual assessment, here's what we do. if we have vectors up in our P could be 100 or 1,000. Nowadays, high-dimensional data sets are very common. We try to make pictures of them. Usually they're scatter plots in 1, 2, or 3 dimensions. Excuse me, my voice is failing. On the other hand, we might have relational. It's okay, I have a Coke here. I'm going to get it in a second. We can have distance data, relational data, and I made these rows red and blue so you can see that. One of the schemes that people used in the early days of visual assessment was they would plot. You're going to see one of these. It's going to come so fast. They would plot graphs of the rows and compare the graphs to each other. So you might see that the red rows look like one type of thing and the blue rows look like another, that sort of thing. So these are called display functions. And as I said in the previous chart, it's usually the case that the right-hand side is more general than the left-hand side. All right. Right, let me put these up and get a drink. Early in the day. So the interesting thing about this chart, to me one of the most interesting things is, probably everyone in the room knows who Carl Pearson is. Is that true? Right, Pearson's correlation coefficient, but did you know that he invented the histogram? And he also invented principal components analysis. These are some very early methods for visual assessment. And then later we have lots of different methods. And now there's a MATLAB toolbox written by one of Jeff Hinton's students that has 34 methods for projecting high-dimensional data into 2 dimensions. I have a picture of some of it coming up. But before I get to that, let's have a look at radar plots, which everyone has on their computer. They call it a different name. This is some data that I took out of Time magazine in 2012. Here it comes. Right. All right, so you look at this. How many clusters are in this data? I mean, you can just look at it and see, right? You can compare the shapes. What is this data? If you look at the top, this is data that compares the taxes, 4 kinds of taxes for each of the states in the United States. So for example, Utah, I don't know if you can see it, right? Individual taxes, sales taxes, property taxes, and company taxes, right? So a state like Utah has a small triangle because the values of the 4 tax coordinates are small, and a state like New Jersey has a big vector, so you see a big patch. So this is a type of visual cluster. Can you see it, Claudio?
Yes, I was looking for California, should be big.
What?
I was looking for California because California should be
California?
big. Yeah.
But this is,
No, that's New Jersey, but I don't see California.
It's
can't
under
see
Utah.
California?
The word Utah under.
Ah, the top, yes, the second to the...
we go backwards.
Yeah, it's also big there. Yes. Up in the top row.
It's there, it's great, it's right here.
Yeah, right. Yeah.
Okay?
Big.
California isn't big for taxes.
It's big, that's big.
No, it's not that big.
The red one.
It's not big compared to some of these others. But anyway, these are radar plots. And if you have data that doesn't have too many dimensions and not too many samples, this is a nice method for looking at it.
Yeah.
It's also called a method of stars, whatever. This thing really drives me crazy. So there are lots of ways to make scatter plots. If you have high-dimensional data and you want to project it down and look at scatter plots. So here's a little section of the MNIST data, which appears quite often in the pattern recognition literature. It's just individual digits, 0 to 9, written by different people, 60,000 samples in this database, but the dimension of each image is 784, so this is high-dimensional data. So if you want to look at it, you can project it into R2. Here are some different pictures of it, taken out of Jeff Hinton's paper. TSNE is a popular method. Salmon's algorithm is a famous old nonlinear method. LLE, linear least squares, isomap. So the point is, these are 4 pictures of the same data set, and the data is labeled, so that's where the colors come from. So if you think that you can see what high-dimensional data looks like by doing this, take another look at this. Because these are 4 pictures of the same data, and they give you very different ideas about what might be in the data. Okay? So, different projections do produce very different visualizations. So how about relational data? So there's a lot of interesting stuff going on in relational data. I have all of these papers. I have images from some of them to show you today. The first computer-generated data images in 1957, Peter Sneese, I believe is still alive actually. A man in the UK who has a famous book with Robert Sokol about numerical taxonomy. So let's have a look. 1873, even earlier than Petrie. Oh, we'll try and come first here. I told you about his book. So here's a data set from Tryon's book. It's 170 12-year-old boys. Excuse me, these are correlation coefficients. So there's nothing along the diagonal. So he just filled in the diagonal by putting the biggest element in each row on the diagonal so that he could get a complete graph. Then he plotted, I say he didn't plot them. Some poor graduate student at Berkeley probably plotted these, who knows? He selected the row with the largest row sum, happened to be J, I believe. It's this one. So I made these plots in Excel, of course. And they just laid them in, I'm sure they laid them out on the desk and they looked at the graphs and just arranged them until they had the graphs that matched each other in little clusters. So you can see there are 5 clusters here. So FPU, these are boys that fight a lot and that are bossy and unkempt. Boys that are attention getting, restless and talkative and so forth. So these are the traits of the 5 clusters. And the heavy lines that you see in the graphs are mean profiles. They weren't in the data set. They're like prototypes. So you have everything here that you need to build the nearest prototype classifier. Hey, we had the...
It's over there.
Yeah, somewhere. It's good. So this is visual clustering in 1939, and you have everything you need. If you now get another row, you can just use your eye to match it to the heavy black lines. So this is kind of nice. I mean, this is nearly 100 years old, 80 years old. Now I come to reorder dissimilarity images. I've always called them RDIs, but the more popular term is cluster heat map in the literature. If you have a set of intensities, you can just dump them in MATLAB. If you just take this little matrix right here and put it in MATLAB, you get this image. It doesn't tell you much about anything, but you can make an image of it. Can you see any clusters in this image? The answer is you can't see any clusters in this image. You need to reorder the objects. When you reorder the objects, you reorder the rows and columns of the data, and that means that the image changes. So if I just reorder this using the VAT algorithm, which I haven't told you how it works yet, but I will, you get this image. So the point is that the dark blocks along the diagonal suggest that there are 2 clusters. They don't find the 2 clusters. Of course, in this little tiny 5x5 matrix, you have the cluster. So that's the whole idea of the VAT family of algorithms. So there are 3 functions that affect what you will see. One, of course, is the way you choose to display the data. The second is how you reorder the data. There are many ways to do this, not just the way I'm going to tell you that we favor. And then there's clustering of the data itself. So this is the first image that I've been able to find of relational data. It was made in 1873 by a man named Boula. 20 neighborhoods in Paris, and he was trying to determine whether the people who lived in the neighborhoods had different characteristics, demographic characteristics. Like people in this neighborhood drink beer, people in this neighborhood eat French bread, whatever. Then he made this matrix. He didn't do any clustering in it, he didn't reorder it, he just made it and looked at it and tried to make some decisions about neighborhoods in Paris. But this was manually drawn and colored by him. It's a long time ago. 1909, Zekanowski produced what I would consider the first cluster heat map. Here's a picture of it out of his paper, 1909 paper. Here's the quote I took out of Zekanowski's paper. And you can see that he already talks about the three small stars and column C black color. So although they're not filled in nicely, you can begin to see the two black sub-diagonals. So this again was manual. Yeah, I was pretty surprised when I saw this. I didn't know about it until 10 years ago. And Zekanowski never gets credit for it, but he's actually the person who invented the minimal spanning tree. If you look back in the clustering history, you'll see that. Zekanowski was an important person. Yeah. Then in 1944, a man named Cattell wrote a paper with this image in it, and again you can begin to see only did the triangle, upper triangular part. And I like to put this code up because it shows, I believe it shows where the term single linkage came from. People have been doing single linkage clustering before 1944, but I don't think anyone ever called it single linkage clustering. I believe it comes right from this quote right here that you see from Cattell. And again, everything is manual, and again, yeah, I was pretty shocked when I saw this. Because I learned all this stuff after we started writing papers about it, and well, you'll see in a second. In 1957, Peter Sneath published a paper with this image in it. So there were 8 intensities. This image was not done by a computer. It was the image was manually drawn. Just a few years later, Floodgate and Hayes published this. Again, you can see the formation along the diagonal of the darker blocks. It's not a very clear one. Manually drawn. Hard to see. Then in 1973, Robert Lang, who's a man that I got data from my own PhD thesis, he published his thesis at Yale, I guess. He worked for John Hardigan. Wrote a paper which has, I believe, the first computer-generated image in it. And I want to point out to you several things about what he had in the paper. The principle used to make the image was the method of overstriking. Okay. How many people in this room know what that means? I know, Keller, I know you know. Really? Claudio, you know what overstriking is? Yeah. But I know your kids don't know what it is because you've never seen it with a laser printer. But when I was a kid, the typewriters had balls, you know, and it would go one letter at a time. It would hammer it and would advance one space, and then you could backspace it one and hammer it again with a different letter, and you could create things like this one in the bottom, right? So Ling used 15 overstrike symbols to build images. I know you don't think, so here's the iris data, just to show you. We're going to see it again tomorrow, I guess, in my talk anyway. This is 4-dimensional data. So this is a plot of the third coordinate versus the fourth coordinate. You can see that there's one well-separated set of 50 plants and 100 that are mixed together. What is it, fire drill?
Yeah, it's happy separate too. It's not real.
Don't worry about it. Okay. I'll remember that when I'm in the hospital. So Ling only used 99 points, and I've never known why he only used 99 points, but I believe it's because the carriage only had 99, the cards he was using only had 99 slots. Cards, you say? What can that mean? So here's the 99 points in random order, and here they are in shade computer, and you can see the dark triangle block. And I took this out of his paper. He said, a Fortran program, card decks and listing can be obtained. How many people know what that means? Keller, don't put your hand up. I know you know. Well, in the old days, you actually had to punch cards to make computers work. This is what these card decks mean. You know, that's the way I learned to write computer programs, with punching card decks. I know, it sounds so crazy. You can't believe it, you can do it on your phone now. All right, so here we are. You think we can catch this kind of fish? Now we're going to talk about VAT and IVAT. Here's the VAT family. So these are people in Australia that I've worked with on some of these papers. Jim Bailey, Jeff Chan, Dheeraj Kumar's in India now, Chris Leckie, Kalani, Lawrence Park is in Sydney, Suzar is in Melbourne, Rao Cunningham is now at MIT, but he was in Australia when we did some of these papers. Here are the US component, including our friend Jim Keller up above, Jackie Hoopan, Rick Hathaway was at Georgia Southern, Tim Havens at Michigan Tech, and Leon Wang is in China, and Anna Wolbeck, I guess, is still in Holland. I'm not sure where she is anymore, but all these people contribute different papers. There are a lot of them now. These are a few of the more representative ones. You see the one right at the bottom is a very recent survey of the VAT algorithm, family of algorithms that Dheeraj and I wrote, and it's just published right now in SMC magazine. So, what is this all about? So Rick Hathaway and I wrote this paper in 2002, and we said our idea was that we should reorder D to D star in order to make groups of objects that were similar look, appear on the vision. It's a big idea. And of course, Zekanowski and Cattell, I discovered long after we started writing these papers, did this long ago. And this illustrates, how many people know who that is? You do? Do you? That's right. Alfred Newman. Well, Newman's laughing at me, and the point of this chart is this quote right here by Hegel. It's called Hegel's paradox, and it's a true paradox. Man learns from history that man learns nothing from history. And of course, this applied to Rick Hathaway and I when we're writing these papers, and it will happen to everyone in this room. And it happens to everyone on this planet, really. So, let me just flash this up. There's nothing magical about this. N comes a matrix that's n by n in size. If it has missing values, we know how to fill them in. It has to be symmetric, and it has to be positive definite. And there's nothing, this is the whole algorithm right here. This is it. So the heart of this algorithm is to build a minimal spanning tree. If I could do this, so it's to build a minimal spanning tree right here. And we just use Prim's algorithm to do that with one small chain. Prim's algorithm starts anywhere, but we always start at one end of the longest edge in the graph. And there's a reason for that. I won't get into it today, but that's it. This is it. There's nothing to this, really. Why do we do this? Well, I guess I could point that out too. What we really want is this sequence of insertion of the edges into the minimal spanning tree. Because once we have them, what we do is, and I think I have this here, we reorder the matrix D by reindexing ij to pi pj. It's really simple. You can write this code in 20 minutes. So that's nice. And even nicer is, there are no parameters. You just do it. And either it works or it doesn't. So before I start this, so where's our Pablo? I don't want to pick on the same Pablo again. How many clusters do you see?
4.
Do you? How many people think there are 4? That's interesting. Clusters mean? You think that's a cluster? Most people would say it's noise or an anomaly or something like that, but I don't disagree with you. I would say there are 4 clusters. If I build a minimal spanning tree on this data, what will happen? Well, if I start here, it's going to connect all the blue points to each other before it goes anywhere else. And then it's going to jump up to here and connect all the red points and so forth. You can see what it's going to do. Can you not? If I start here, it's going to connect all the green points first and then hop to a different place. The point is, when you get done with that and you reorder the input data, if I just start anywhere and do a random edge sequence, I get this image. But if I start and do the minimal spanning tree reordering, I I get this image, and that image tells me exactly what's in the data set. You can see this one point right here is this pixel right here. Okay? So this little simple toy example, of course, tries to say to you, oh, we should always do this. Well, it doesn't always work, but it works sometimes. We have a much better one than this, which you'll see in a minute. So now we're going to talk a little bit about single linkage clustering. So here, a pair of subsets. The distance between them is defined as the distance between the two closest points. Single linkage is good for chains. It's not good for clouds. And the reason it's not good is you can hop across like that if there's a bridge between the various clusters. So single linkage, minimal spanning tree, and that I've had. Here's 100 points. We'll see tomorrow, I guess, where it comes from. Here's the IVAD image of it. All right, I look at the dark box. I see that I can cut it in 9 places. It means there's 10 clusters, or it suggests there are 10 clusters. Here's the minimal spanning tree on the points. The green edges are the connection points. I cut the green edges. I cut the green edges, and I get this partition. And that's how single linkage clustering works. That's all there is to it. All right? It's not complicated. Doesn't always work. Sometimes that doesn't work. All right. Pedro. Is there a Pedro in the room? No Pedro? No? Is there a Pedro?
But you can choose also Maria.
Maria. Maria.
Maria?
There must be a Maria. But the Marias they don't want to put their hands on it. I understand that. Okay, Pablo, how many clusters?
Wow.
Dos.
Dos?
See. However, VAT fails to see that. Right? And there's a reason for that. And you would say, oops, well, we can fix this. And the way we fix this is to transform D to D prime before we make the image with a minimax path distance. So I have a little picture here. Let me just put it up. Get my thing here. So here's vertex I and vertex J, and the input distance is Dij between this pair of vertices or objects. If there are other paths through the graph that will go from I to J, I find every path, I find the biggest distance along each path, and I aggregate all the maximum distances, so it's M1, M2, and Dij, and I take the smallest one. And I replace Dij by the smaller one, if there is a smaller one. It's a feature extraction, nothing more. So, here's the IVAD algorithm, and it's, I means improve. There's nothing to this one either. It's recursive. There is an iterative version of it that's O(n) cubed. The recursive version is O(n) squared, and it works like pretty well. So here are, come on. Yeah, if I say 1, will I get anybody, Pablo? Let's say 1. Come on, there's some 1s in this room. There must be. But they're all terrified. They're all terrified. They're terrified. There's a 1. None of them want to admit it. Okay. 1. How many clusters here? Yeah, see. Okay. So the input data sets are at the top. And the VAT images are in the middle, and you can see that the VAT images don't show you much about the structure of the data, but the IVAD images in every case are really nice. For example, if you look at this one, there's 5 clusters, and you see that there are 5 dark blocks, and the big stripe is the big block, and so forth. All right, so this is an idea how that works. We can do outlier detection. Here's a big set of neuron spikes. These are 48-dimensional waveforms. These are the mean spikes for each of the labeled clusters. There's an anomaly, an anomalous spike. We'll see that we can see that. There it is right there. Z4. In the entire data set, the whole set of spikes is anomalous. So you can see anomalies using this sometimes. You can't make a dendrogram for this, for 4600. You can make one, but you can't see it. But you can make a dendrogram of the 10 points. Here are the 10 mean spikes. And here's the outline image of them. And you can see, for example, before I put this up, can you see that these two are grouped together, 6 and 10, visually? Well, you can see they're grouped together here. They get joined together in single linkage right away. So that's the point. You can see that the outline image looks like single linkage. It's like a visual front end, single linkage. You can do the same thing with inliers. Here's an interesting data set. I know not many of you are cricket fans here in Chile. Does anyone even know what cricket is? Okay. So this is an interesting data set. These are 12 umpire signals that are done by 4 actors. There are many more than that 12 signals, but this is a data set you can get on the internet. So can you see clusters in the data? Well, maybe, maybe not. If you just make an image of this data set without ordering it, it doesn't look like there's much of anything in it. But if you order it with that, it looks like this. So the one-arm signals are 5, 6, 7, 8, 2. The two-arm signals are the 6 in the bottom. And there's an intermediate signal, person 4. And here's the dendrogram of it. You can see again, the one-arm signals are on the left in the dendrogram, and the two-arm signals are on the right, and 4 comes in last. They can sometimes detect inliers that way. Great Barrier Reef, Australia. Weather station, sensor nodes on Heron Island. 3D data, that's one of the nodes. This is fairly old now, 10 years old data, but I like to use it. Jim, I don't know if Jim Keller will show it again or not. I'm going to show it both today and tomorrow. So there was a cyclone just off the coast of, or a hurricane, we call them on the northern hemisphere, just off the coast at Heron Island, Cyclone Hamish. Later we'll see a movie of that. Later, I don't know if that's this afternoon. Here's the Heron Island 3D data. You can see the anomaly in it. This is the anomaly. This is the cyclone. You can see it. IVAC can see it. Single linkage can see it. Grand St. Bernard data set. 17 stations in Switzerland. Same sort of data, a different type of anomaly. This right here, drift. Drifting at one node. You can see it with IVAT. You can see it with single linkage. All right, so there are different types of anomalies that you can detect with these visual methods. These data are ellipses. There are 4 kinds of ellipses here, green ones and blue ones, and these 2 red ones are anomalous to the 2 clusters of ellipses. Again, you can see it. There are the 2 red ellipses. If you did fuzzy C-means or K-means or something like that on this, you would not see this. You would see something like that. You would only see 2 clusters, not 4. All right, IBRL data at Berkeley. Where is number 17? 17.
Not to the right.
I think there's an anomaly at 17. So this is 2D data. Again, this is just off the internet. Here are the ellipses, 1 ellipse for each sensor. Pre-clustering estimates of C, 2. IVAT C is 2. Post-clustering, single linkage C is 2. And there's the single linkage 2 partition. All right. And now we're going to talk about big data and sampling things. What time is it, Pablo? How much time do I have left?
Still have, we are part of your time.
What?
Still 40 minutes. 40 more minutes.
40?
Yes.
40?
Yes. Go ahead, go ahead.
Okay, we're in good shape then, I guess. 63, there's only 95. Now I'm going to talk about maximum directed random sampling. So here's the big data gang, slightly different gang. So let's see. So who is this gang? So there are a bunch of people from Australia again. Nick Pell, of course, current president of our society, is in India. Palani, Raul Leckie are in Australia. Jackie Huban's in Virginia. Tim Havens, I told you about Punin. Who's Larry Hall is in Tampa. And Dheeraj is in India now. So these are the main people in the big data gang. And again, there are a bunch of papers that are available. I'd be happy to give them to you if you want them. So here we go, maximum sampling. So here's the sequence in the history of maximum sampling. The person Thorndike, again, when he wrote this paper, Who Belongs in the Family, defined maximum sampling. I'm going to show you the description of it by Casey and Nodge, 1968. So through the years, it's appeared in various papers, in various ways. In 2006, Rick Hathaway and I proved 3 theorems about maximum sampling that I'm going to tell you in a little while. And lately, this is 2016-18, there have been a couple of approximate maximum schemes, not maximum DRS scheme. So maximum sampling, what is it? So let's just read this. First sample in the batch, you just grab it, you measure the distance to all the other samples in your data set. And you take this, they were looking for prototypes or cluster centers, you take the furthest sample from the one you started with as the second prototype. Now you have a pair, you measure the distance to all the data points from the pair, and you pick the one that's furthest away from both of those. You just keep going until you have the number of samples you want. So this is a nice adequate description of it. I have a picture of how it works. And the selection rule is just what Casey and I said. So you just grab the first sample in the data set, measure all the distances, the second prototype there, you measure the distances again, you pick the third one like that, and just go until you have the number that you want. It's a very intuitive idea. Obviously, it depends on the way you measure distance. You would think it would depend on the sample that you start with, but Jim Keller and I and a student of his just recently conducted a study about different ways to initialize. There are 6 different ways in the literature to initialize maximum sampling, and we decided, and I guess showed empirically that you might as well just start with the first sample in the data. You can't do better. So, and it's the easiest too. Here's the maximum sampling algorithm. Look how hard it is. 9 lines of code. So I don't know, somebody's going to talk about deep learning or something where there's 1 million lines of code, right? These is, yeah, I'm old, so I do simple stuff. Anyway, this is how you get it. Notice that C prime, we call C prime, this is the number, let me just point this out. C prime is a desired number of maximum samples. Hey, you can have it, you don't have to write it down. I'll send you the slides, no problem. So now it comes to maximum directed random sampling. So now you have the maximum sample, what happens next? So Hathaway and I and Jackie Huban said, let us take the C prime maximum samples and construct the k-means crisp partition of the whole data set. It could be time consuming, so here's a picture of that. So here's the first cluster, the second cluster, and the C prime cluster, right? So the maximum samples are the ones in circles, and now what you do is, what do you do next? So now you have all of the data grouped into C prime clusters, and you randomly sample each of those C prime subsets this many times, NT. T for the teeth one. Notice the ceiling function here. So this is the cardinality of the teeth subset divided by the total number of points in the sample. So this is going to be NT is going to be a fraction of NS. And because of the ceiling function, it may be that NS is not exact, It's just approximate. So you just grab some samples from each of these things. And the ceiling function tells you that this is could just be an approximation. These are directly random samples, and they're actually a little better than real random samples because you're drawing a certain number of random samples from each subset. See the difference? If you didn't use the partition, you just shut your eyes and collect NS samples from the entire data set. So the word directly is important here. The maximum sampling is not as accurate as random sampling, but random sampling is not as accurate as directly random sampling for the purpose of clustering. All right, here's the other half of this. Again, this is not rocket science, this is computer science, I guess. Now I have to tell you about Dunn's index, one page about Dunn's index. So Dunn wrote a paper in 1973 and said, let us do the following thing. We'll start with the diameter of a cluster or a subset. This is crisp. We'll measure the single linkage distance between pairs of subsets, and we'll form this, he said, just form up this index of separation, which now is called Dunn's index. So in the top, you have a bunch of single linkage distances. In the bottom, you have the diameter. So, you know, if the biggest diameter is small, that means the clusters are compact, right? And if the biggest separation is big, that means they're well separated. So this is a function that measures compactness and separation. It's called a cluster validity index. And Dunn used it to define the notion of compact separated clusters. And then he proved a theorem that said the input data has compact separated clusters if and only if this number is greater than 1 for some partition of the data set. Some partition. So why would I show you that? Now we have 3 theorems about this type of sampling that are related to Dunn's index. And those 3 theorems are this. Hathaway and I and Jackie Hubin published these 2 papers at the bottom. The first one says, if there is a CS partition of the input data, then the maximum algorithm will select at least one object from each of the clusters. Second one is MMDRS1. If the ceiling function can be ignored for all C prime of the subsets because they're all integers, then the proportions are exact. And the third theorem is if Xn has CS clusters and C is equal to C prime, then MMDRS will produce the CS partition. These are not strong theorems, these are weak theorems because in the first place it's really hard to know if you have a compact separated data set. In the second place, not so many data sets have this property. But it's all that I know about that gives you any guarantee that the sampling strategy you use produces things related to clustering. So here's the banana data, 50,000 points in R2. There are 50 maximum samples. And on the right, C prime is 5, there are 50 MMDRS samples. And on the left, you see there's a 1733 split, even though there are an equal number of points in both distributions. And on the right, it's almost even. So even though the one on the right looks worse, it's a much better sample. And the IBAT image shows you that. Okay. So what do? You have this input data set, and it's huge, 10 million by 10 million. You do this MMDRS sampling, it gives you the objects that are selected, and from that you have NS and sub-S samples, and you can use those to make approximate cluster heat maps, or if you're doing clustering, over here on the right, you can actually take the samples and tomorrow we'll talk about taking these samples and doing sampling plus extension for big data clustering. Think you can catch one of these, Pablo? So, I'd love to show you that. How long do you think this fish is? Say in meters. Think it's 1 meter? 7 meters. Well, Lena and I were walking down the street in Tainan. I saw this sign. I thought, I have to have a picture of this thing. It's huge. There's no way to see the scale of it. You know, it's the width of this, almost the width of this room. Anyway, that's a nice fish. So now we're going to talk about scalable IVAT. We're almost there, Pablo. What does this mean? If you have a big data set and you want to make a cluster heat map of it, how will you do it? Well, you can guess the way you're going to do it. The way I'm going to do it anyway is to first run the MMDRS algorithm and then make a cluster heat map of the NS samples that you have. And so here are some examples of that. So this is not a big data set. This is 5,000 points. If you VAT it, this is in the old days, you get that picture and it tells you that, oh, I should have asked somebody. If you SVAT it, scalable VAT it, so let me just put these up here. The point of this picture is this. It takes you 156 seconds to get this image, and it takes you 0.3 of a second to get this image with 2% of the data. And this image tells you that basically gives you the information you want, which is how many clusters to look for. This is just to test whether the sampling scheme actually works. So here it is for a noisy data set, and it's basically the same kind of picture. All right, so we can VAT it. Now we're looking for 100,000 points in R2. There's no way to make a VAT or an IVAT image of that. It's too big. IVAT is limited to about 10,000 points. So you can load it, but you can't make a VAT or an IVAT image. But you can still do SVAT, and there is the SVAT image for 500 points. Yeah, I don't know why this is making noise. You can see it. I mean, it's hard to see. It's harder to see, but you can still see there are 3 clusters in the data. But it suggests there are 3 clusters in the data, so that's good. And then there's another transformation besides the minimax distance transformation based on spectral feature extraction called eSpecVat. So here are 3 million points in R2. And here's the SpecVat image of 2,500 of them. So you can see that this image here, built with 0.08% of the data set, contains the information you're trying to extract about the data set. There's a different picture. These are from the Berkeley Image Segmentation Database. Here are the SIVAT images from 300 pixels of each of those images. They suggest the number of clusters or segments in the image to look for. And here are the segmented images. And these are not difficult images to do. This one, for example, only has three shades in it. It has the dark entranceway. The medium gray is the church. I guess it's a church itself. And then it has the sky. And so this 300 pixel cluster heat map of it tells you there might be 3 segments in the image. C equals 3, and here is the segmentation of it. It looks okay. So again, this is just an example of the way you want to use this type of assessment. Now for this one, Pablo, you'll have to come to my house, because this is a fish I caught in my backyard. Well, in the water. And that's my dock right there. We're almost done. I'm going to talk very briefly about incremental IVAT for streaming data. Jim Keller is going this afternoon, I believe. You're going to do the streaming data talk this afternoon, right? So Jim Keller is going to give you a very extensive presentation about clustering type algorithms using streaming data. I'm just going to show you right now how to build IVAT images of them. So the idea is simple. Suppose you have 9 points coming in. They arrive at times 1 through 9. There they are. They happen to be arranged into 2 clusters. Suppose you have a 7 by 7 sliding window. The first 6 points arrive. Inc means incremental. There's inc IVAT and dec IVAT, increment and decrement. The 7th point comes in. Here it is right there. The idea is that you will see that displayed in the ink of that image. Now this is a sliding window. Let me go backwards. There's only 7 points in this image. So when the 8th point comes in, you have to take 1 point out of the spanning tree and stick a different point in. And it's not such a trivial thing to figure out how to do that. It looks trivial on this slide, but it's not trivial at all. So X8 comes in, X1 is deleted, you get an image like that. So this just shows you how it works. That's just the philosophical basis of it. Now, I don't know if I'm going to be able to do that. What's going to happen here? This is a movie. But it's not a movie that's going to run. I don't know how it's going to run. Here. Yeah, it's running on my computer, but not. Yeah, okay, started. Now it's going. All right, so this is the Heron Island data. Remember that cyclone. One day, let me help it out a bit. It's 9 minutes, so we don't want it to go all the time. Yeah, I know. But I want to help. I want to get it. You have to start it again. Yeah, okay, we'll see. Look. Let it go for a little while. The data set's coming in here and it's building this image right here. And you can see that the IBAT image is changing as the data set comes in. Pretty soon the Heron Island Hamish is going to start. Pretty soon. I don't know where we are in time here. It starts at 1:25. It'll come in. We're not going to run the whole thing, just so you get the idea. So, I say it's going to come in. It's so suspenseful. Will it or won't it? Oh, there it comes. Here's see the red, right? And there's that, so it's just going to keep going like this. Now the data's going to keep coming in, and in a little while there's another anomaly, because there was a temperature anomaly that will show up down here, and it can run all the way to the end now. You just push it to the end. See, there's two anomalies, and they will persist in the iPad image to the end of the data set. So we stop that one, go to the next one. Just go to the next page. Yeah, that one should run by itself. So this is a neuron spikes. You can see these coming in. So as the data set evolves, so does the IBAT image. Big push that to the end, because there's nothing. It just keeps going, right? Gets the end just like that. Go to the next page. Right. Okay, so are we back on this thing now? Yeah. All right, so Dheeraj Kumar was the guy who figured out how to do the insertion and deletion with a sliding window. And then Punin and I decided that would be better to try to work with chunks and not have a sliding window, so you could go all the way across the evolution of the stream without losing what you had seen. So this is a data set that Punin invented that comes like this. The first 50,000 points in it arrive 12,000 in one subset, then 12,000 next, and so forth. So you see the picture of it. There's the first 12,000 come in, but this is because the sliding window approach has a 5,000 point sliding window. You can see that it looks okay here. This is the time. 1 to 5,000. But the next one, right, this is the time 1 to 12,500. So the second subset is just starting to come in, and it shows up okay. It shows up okay here, but it looks like 2 equal-sized clusters. Now there are 4 clusters at 48,000. You can see them in this chunk image, but you can't see them in this because the sliding window only sees the last 5,000 points. Now at 50,000, in comes this little data set in the middle, and you can see that this little pixel right here is seen in the chunky IVAT, but it's missed completely in the original ink IVAT and deck IVAT. So then what's going to happen is, excuse me, 25,000 points are going to fill in between these two clusters, and then 25,000 points are going to fill in between these two. All right, so this is what the data set looks like. So you can see that, again, because the sliding window only has 5,000 points in it, you don't see this structure here, but you do see it here. And here you see there are 3. Right, this little pink set is still this one and persists in the middle. So this sequence of images is limited because it only uses a sliding window of 5,000 points. Right? Whereas this sequence of images persists all the way through. And I actually have a movie of this as well. I don't know if it's going to run. Is it going to run? Oh, what would I do without you, Pablo number 3? Here we go. This runs pretty fast. How much time do we have, Pablo? Number 1?
You have 20 minutes.
Plenty of time.
Yeah, 20.
And deal all of this. So this is the middle point coming in. You can see it right there. The left side fills in, the right side fills in. Yeah, okay. I'll go to the next page. This is a different one. So you get the idea, right? I got one more, I think. The KD cup data. Okay, run that one. So people do streaming clustering love this data set because it's real, although it's in some sense artificial, it's intrusion detection, which is a real, actual good problem that would be nice to solve. And so the people who do streaming data analysis like to use this data set. This is a 10% data. There's 4 million samples in the original data set. And you can see it's running pretty fast. This data is 41 dimensional, so it's a pretty high dimensional data set. And there are actually only 5, you see here there are 5 real clusters, but the normal data occupies 20% of it, and these 4 here are broken down into 22 kinds of service attacks. I think we'll see an SI that image of it. There, so this SI that image for 230 points, you can see 5 clusters. I'll see it again. Okay, so that's it. We're at the conclusion, so that's a happy word for you, I know. All right? You know, if I was out there, it would be a happy word for me. Yeah, you're smiling. Why shouldn't you? Why use visual methods at all? So, I mean, this stuff is, there's a good reason beyond the reason I'm going to tell you, which is it's a lot of fun because you can see what's happening, right? It's not like running a deep neural network or something where it all seems like magic, right? When you do this visual stuff, you can see it. And humans are really good at it, as Pablo told you, right? This is what we do, pattern recognition. But just to give you the justification given by the academics, here's a quote from Ronald Fisher. She's almost 100 years old, from his famous book, Design Experiments, right? Diagrams prove nothing, but they bring outstanding features readily to the eye. All right? I believe that, 100%. And then much later, Brian Everett, in his little book, Graphical Techniques for Multivariate Data, said basically the same thing. He said, don't ever think that you've got the final answer by using a visual method. You should always couple it with some kind of analytic technique. I agree with that as well. All right? What you're trying to do when you use visual method, just get a sense of what might be in the data. That's the whole point of it. And then, if you're interested in papers, this is now 11 years old, this paper. In 2008, Weinstein published a paper and claimed over 4,000 publications had cluster heat maps in them in just this one set, one small subset of the literature. You can find cluster heat maps everywhere. Chemistry, statistical mechanics, physics. They're usually, I mean, the weather, when you look at the weather on television, right, they show you radar plots of the storm cells, they're cluster heat map. They're everywhere. And then, of course, there's Lewis Carroll. It's Alice in Wonderland. How many people have read that? Not so many. Some. Right? So what's the use of a book without pictures? And then lastly, there's Edward Tufte, who said, as for a picture, if it isn't worth 1,000 words, to hell with it. Right? And with that, this is my son Eric. You can see me, the coach of the team. What? An American interested in football? How is it possible? Well, the other principals in this picture, right up in the back of the room. Wait for it. I think this is going to work, Jim Keller. Wait for it. Okay, that's it.
Thank you, Jim, for your wonderful presentation. So we have time for questions.
Stay nada.
They're not done. Questions?
You see?
Any questions?
This is my
He
prediction.
told me in the prediction at the beginning there would be no questions. So please, please,
No, it's
¿Puede
okay.
ser en español?
The question is it time for coffee?
So
Right?
let me start with a question so that people can have some time. Okay? So here you see, oh, there's a question. Great.
Where is that question?
Could you, I will ask you for your question, please. Abran fuerte, para que él escuche bien. Si no, no va a entender. Abran fuerte. Okay.
Ya, ¿se escucha?
Sí.
Sí. ¿Cuál fue la etapa más difícil para poder discriminar los datos al momento de usar la transformada?
What was the most difficult part? ¿En cuál programa?
Porque utiliza diferentes transformadas para poder discriminar los datos, o sea, los clusters. Entonces, mi
What is
pregunta...
the most difficult part when you want to discriminate among the data?
What is the most difficult
Part. Yes. When you want to discriminate, you have these different clusters.
Yeah?
What is the most difficult part?
The most difficult part is to choose the correct number of clusters to look for. Why? Every clustering algorithm will do its job. Every one of them will produce clusters for you. If you use 100 different algorithms, you may get 40 different solutions. It's too bad, right? That's the way it is. Okay?
Okay, there is another question there.
No.
Yes. There are two questions.
Yeah, but you forced them to ask this question. They know. They probably have posters tonight.
I win $1.
It's arranged. So for which kind of data sets this method doesn't work? Because you show like different type of data set. So have you tried with like categorical data, textual data?
I don't hear one.
Oh, okay.
That's why I'm looking at you.
Okay, so the question is that this work with different kind of data like categorical data, text data, and that
Or just numerical data?
As long as you can make a dissimilarity matrix out of it, it will work. Now you can.
Yeah.
I mean, it may work. Well, this is true of every pattern recognition algorithm. They all fail sooner or later. They all fail.
Same question.
Yeah, poster.
I have a question. When you say at the end of your presentation that you needed more than one visualization algorithm, how many do you recommend?
The question is that he's saying that you recommend to use more than one visualization algorithm. How many?
I always think you should try at least one probabilistic method, like EM, one deterministic method, like any of the C-means models, possibilistic, fuzzy, or K-means, and a single linkage. I always try at least those three. Yeah.
Any further questions?
You probably beat them to death already.
You are dead already, he's saying. No?
Coffee. Cerveza.
Okay. May I have a last question?
Yes.
Okay. So you see here many students. So many of them are undergraduates.
Yeah.
Probably just starting with machine learning and computational intelligence. So what would be your recommendation to start looking at clustering methods? To study beyond your talk, of course.
I know this about these students. None of them take enough mathematics. That would be my advice. Take as much math as you can. Because no matter what, the math is underneath all of this stuff. The more of it that you learn, the better off you will be. That's my advice.
Good advice. Okay,
Especially if you love math.
let's ask the speaker again. Coffee time.
Coffee time. Rushing out of here.